All right, so today we are talking about the fundamental counting principle, which is very self intuitive. It makes a lot of sense. It's not something that we usually have to teach for very long before people go, yeah, that just makes sense. You can use the counting principle to find the total number of outcomes. If one activity can occur in M ways and another activity can occur in N ways, then both activities can occur in M times N ways. So you find the product of the two number of ways. To leave her office, Karen can choose between 3 sets of stairs and 7 doors. How many ways can she leave her office? So the first decision is which set of stairs. So there's 3 sets of stairs she can choose from. And then once she gets down to that floor, there are 7 doors she can leave from. So 3 times 7 would make 21 possible paths to leave her office. Number 2, a sweater comes in 4 sizes and 8 colors. So the first choice is what size? Okay, so 4 sizes. So there are 4 choices. And then 8 colors. So times 8, 4 times 8 would be 32 possible sweaters. Now, I did work in a factory where we picked things like sweaters to get mailed out to customers. And you have to understand that that means that sweater, which comes in 4 sizes and 8 colors, there's actually 32 bins of that exact same sweater. But you have to make sure when you go to pick one that you pick the right size and you pick the right color out of those 32 bins. So this does have a practical application when we're talking about real world. Like that one sweater in a catalog or on the internet is going to take up 32 bin spaces in that factory. The section that I worked in was about 3 football fields. A class has 11 boys and 16 girls. How many ways can the teacher choose one boy and one girl? So let's say we're going to send representatives down to the office, and every day we're going to send one boy and one girl. There are 11 boys to choose from, 16 girls to choose from, 176 kids to send down. Now, I don't think this is a fair way to do it, but there's 176 ways to send one boy and one girl. A dinner menu consists of 5 appetizers, 12 entrees, and 3 desserts. How many ways can someone order 1 appetizer, 1 entree, and 1 dessert? So let's say we were going to do a tree diagram of this. We would have 5 branches for appetizers. Off of each of those 5 branches would be 12 branches for entrees. And off of each of those 60, because now we'd be at 60 branches, there are 3 branches for desserts. We would have 180 possible outcomes, ways that we could order an appetizer, an entree, and a dessert. Now, I can go down through the rest of these. They are, I would say, pretty self-explanatory. I think it gets a little bit tricky maybe when you get to say a quiz contains 5 multiple choice questions. Each question has 4 answer choices. Now, this says 4 to the 5th. Now, the reason they've gone with an exponent is because you have 4 choices, 4 choices, 4 choices, 4 choices, 4 choices. So you have 4 choices 5 times. You could have written out 4 times 4 times 4 times 4 times 4. The way the previous question wrote out the tens. 4 to the 5th, a little faster. 1,024 ways that you could, I guess the answers to a multiple choice quiz that had 5 questions, 4 choices each. Number 10, the library codes their books using 2 letters followed by a digit 0 through 9. So there are 26 letters in the alphabet. You would need to know that fact. Times, there's still 26 letters in the alphabet. If the first letter is a Q, the second letter can still be a Q. And then times 10 possible digits, giving 6,760 choices. Now, this is most closely related to our license plates. And the state of New Hampshire a while back went from 6 spaces on the license plate to 7 in order to give more options. And we've got some choices on the back here, or examples. 11, Patrick is buying a new car. He can choose the body style, color, and engine type. There are 54 ways he can select a car with 3 body styles and 2 engine choices. So 3 was the body styles. We don't know the number of colors because that's the question, how many colors are available, times 2 engine choices equals 54. And you've got a very simple one-step equation where you divide both sides by 6 and get that there are 9 colors. At the school cafeteria, you can choose 1 sandwich, 1 snack, and 1 drink. The number of drink options is equal to the number of snack options. So we know that these 2 things that are missing when we get to the question, how many drink options do we have, they have to be the same variable. So I had 63 ways to choose your lunch, 7 sandwiches, and then times X drinks and times X snacks. So 7 times X squared, going to be a 2-step equation. Divide both sides by 7. We'd get X squared equals 9. Square root both sides. So don't forget on that step, you would do the square root of x squared and the square root of 9, and x equals 3. Now, the reason we only use 3 and not plus or minus 3, we can't have negative 3 drink options. Most of the time when we're doing real world examples that involve square roots, we only use the positive square root. So some probability examples. How do we link up counting principle with probability? A coin is tossed 3 times. What's the probability of getting heads just once? So possible outcomes, there's 2 outcomes the first time I flip, 2 outcomes the second time I flip, 2 outcomes the third time, with a total of 8 outcomes. If I only write out the favorable outcomes, if I only write out the ones that have heads just once, that's 3 out of 8, and I don't need to write out all 8. A month is chosen at random, then a standard die is rolled. What's the probability of getting February, then a number less than 5? So instead of writing out all 72 outcomes or a tree diagram, we can say 12 months times 6 numbers on a die, that's 72 outcomes. That's our denominator. And then if we write out February 1, February 2, February 3, February 4, those are all the Februaries with a number less than 5. That makes 4 favorable outcomes out of 72 possible outcomes, or 1/18th in lowest terms. Again, remember I said the card from a standard deck is chosen at random. That is information you should know. If you don't, I'm sure that it would be easy to look up what a standard deck looks like with face cards and colors and suits. So after we choose a card from a standard deck, then a coin is tossed. What's the probability of getting an ace and tails? So there are 52 cards in a deck times 2 outcomes for heads versus tails, making 104 total outcomes. Well, if I want an ace with tails, there's an ace of hearts with tails, ace of diamonds with tails, ace of spades with tails, and ace of clubs with tails. That's why we would need to know what the suits are, what the colors are, what the face cards are, what does a color look like, what does a suit look like. 4 possible favorable outcomes out of 104, or 1/26th in lowest terms. A standard die is rolled 2 times. So I get a 6 the first time, I get a 6 the second time because none of the numbers disappear. Every time I roll a die, there are 6 outcomes, making for 36 outcomes from rolling it twice. What if I want to get a 1 both times? Sometimes that's called snake eyes. There's only 1 out of 36 ways to get that. For questions 17 and 18, we've got 2 spinners, and it says each spinner to the left is spun once. So we're going to spin a color followed by a number. What's the probability of getting yellow and an even number? So yellow 2, yellow 4, yellow 6, yellow 8. Those are our favorable outcomes. And there were 5 choices on the first spinner times 8 choices on the second spinner, making it 4 out of 40, or 1/10. What's the probability of getting orange or blue? And a multiple of 3. So again, the same 40 outcomes are possible. Orange or blue, I've got 2 choices. So it could be orange 3, orange 6, and multiples of 3 are only 3 and 6. And then I could get blue 3 and blue 6, which also makes 4 out of 40, or 1/10. So the counting principle itself, very simple, very straightforward, can be used often for the denominator when we're doing probability.